All right, so our next speaker is Antonio Mezzacapo. Dr. Antonio Mezzacapo is a principal research scientist for IBM based in Georgetown Heights, New York. He's currently the technical lead responsible for applied research in quantum computing. He has worked on a variety of topics across the quantum stack at IBM, from device modeling to quantum simulations. Let's welcome Antonio to the stage.
Thanks. Thanks, Borja. I'd like to thank the organizers of this workshop and in particular the University of Tokyo for having me today. And I hope that by the end of this talk I will convince you that using classical computations alongside with quantum computing, it's a good idea. So let me start with a high-level motivation, and then I will go through some practical examples of hybrid quantum classical computation. So why, for each one of those examples, I'll tell you why we think it's a good idea to do this kind of hybrid computations. Right, so why is classical computing needed in a quantum algorithm, right? So sometimes there's nothing else we can do because we just have to deal with big classical data, right? So here's some examples of use cases for that, but sometimes we have to read that data, we have to process that data, and eventually, if we want to load it efficiently in a quantum computer, we have to compress that data. So we need that. We need high-performance classical computations. Some other time, we want to warm start quantum computations, or we want to post-process the outcome of a quantum computation with massive classical computing, right? So, for example, this could be the case of if you want to start a many-body system quantum simulation. We'll like to initialize that simulation with a very good classical starting point. Or, as Jay mentioned before, sometimes we want to just optimize the compilation of big quantum circuits so that they can be more efficiently executed on the devices that we have. And then there's a third category, which is we are thinking of building quantum classical workflows. So in this third category, there's not just one contact point between classical and quantum computation, but the quantum and classical computer interact many times through the workflow that targets a certain task. So you can think of this third category. Within this category fall all these ideas that we have seen about circuit cutting or knitting, or if you want, the simplest example of this category would be just a variational quantum eigensolver, whereas the outcome of a quantum computation is fed into a classical optimizer. So these are the high-level categories, and then I'm gonna tell you about some examples, some use cases of hybrid quantum classical computations, and why classical computing sometimes plays a major role in helping quantum computing achieving certain tasks, right? So probably the simplest, most paradigmatic example of mixed hybrid quantum classical computations is the variational quantum eigensolver. I think most of the audience is familiar with this concept. Here we're trying to optimize a cost function, and the value of that cost function obtained with a quantum computer is fed to a classical optimizer, and there's a feedback loop until that cost function gets to an optimal value, right? So here the classical computation is very simple, but nevertheless it's an example of workflow interaction between quantum and classical computers. Let's take it a step further. What we could do, imagine that you have a quantum computer of n qubits, and now you're trying to optimize a quantum cost function on these n qubits. So what we could do is use a quantum computer of half the number of qubits to execute the same computation, so to optimize that same cost function. So how do we do that? We could split the quantum system into two subsystems. So here is system 1 and system 2, and we can execute quantum computations on these two different subsystems and then correlate the outcome of these computations with a classical computer. And going more into the details of this, if you have a quantum state, you know that the entanglement, we know that the entanglement of that quantum state across these two subsystems can be captured by its Schmidt decomposition along this partition. And then what will happen is that a classical computer will sample from a probability distribution that captures these Schmidt coefficients, and to see the the start of the quantum computations across these two subsystems, and so that the output will be the output of this quantum classical computation will be stochastically equivalent to run an initial a big quantum circuit on n qubits, right? So this is how the math looks like. So we have a classical instrument that samples from these Schmidt coefficients, and then we use a quantum computer to estimate observables onto the two separate subsystems, right? So where's the hard classical computation here? It's the sampling of these Schmidt coefficients. So one way of doing this sampling, and this is what we did in this paper, would be just to hard code that probability distribution to sample these coefficients from. But another way of doing this sampling, and actually we did this in a follow-up work, would be to use an efficient classical instrument to sample from this probability distribution, such as a neural network, for example. And if this probability distribution is big enough, you can see that how high performance quantum computing can come into play. Right? And this is the results that we obtain on hardware. This is a simulation of a water molecule obtained using this entanglement forging method, and you can see that so the simulation gets better as we increase the number of bit strings that we sample from. So that number of bit strings captures how big is that initial distribution of Schmidt coefficients we are sampling from. Okay, another idea that has been mentioned before is this idea of circuit cutting. Here, the idea is that we have a big quantum circuit, and we want to execute that big quantum circuit using smaller quantum computers. And so we can do that by cutting the big initial circuit into different subcircuits, and then we can execute the smaller subcircuits on smaller quantum computers. And then the idea is that each one of these subcircuits will depend on where do we cut the initial circuit, and a classical post-processing of the outcome of the executions of each one of these smaller subcircuits will be used to stochastically retrieve, stochastically simulate the outcome of the initial circuit. Right? And again, so here, for example, we will need high performance. So an entry point for high performance quantum computing here will be to optimize where do we want to cut this big circuit. For example, since this method scales exponentially in the number of cuts, we would like to minimize that number of cuts and still be able to cut our big initial circuit in the number of subcircuits that we want. Right, so that's a very hard problem, and classical computing can come to the rescue. And here you see that the amount of classical resources that is necessary to optimize this cutting and post-process the outcome of the small subcircuits increases exponentially with the circuit size, but nevertheless, this exponential scaling is less expensive than just classically simulating the initial quantum circuit. another idea, we can post-process the outcome of a quantum circuit with a classical instrument, classical computational instrument such as a neural network. So here in this work, what we did was we took circuits that were producing approximate ground states for some molecular systems, and we fed the outcome of quantum measurements on these circuits to a classical model that a classical neural network model that was encoding a quantum state, so the so-called neural network quantum states. And the advantage being in using this framework is that if we try to estimate complex quantum observables onto the original quantum state using this framework, then the estimator that estimating these complex observables through this classical tool was giving us a estimator with much reduced variance. Okay, and then we observed this. So these are the numerical results. So what we observed is that as a function of the number of measurements that we took on the original quantum circuits, if we were just to use a naive quantum estimator, then the probability that one of our energy estimation on this approximate ground state for a molecular system to be within chemical accuracy to the true value, you see that this is the line for the naive quantum estimation would require much more measurements to get within probability 100% to be close to the exact ground state, whereas using this estimator through a neural network, we get there much faster. So like something like 3 orders of magnitude. But then if we start to use this kind of ideas, so we start to mix quantum and classical tools, then we have to be careful because not every quantum state obviously can be captured efficiently by a classical tool. So what we made sure of is we did some numerical calculations and we're trying to estimate what's the power of these classical ansätze in capturing ground state or molecular systems, and in this other work, and we found that they were pretty good, and for some molecules we even observed improvements on the existing classical methods. Again, here's another example where classical computation can come to the rescue by improving the precision of these estimators for quantum observables. Another idea is this idea that many computational physicists or chemists are familiar with, is the idea of trying to figure out, if we have a big system, or trying to figure out what are the degrees of freedom, the quantum degrees of freedom of that big system that require more accuracy. So in order for a property of the big system to be captured with overall very high accuracy, right? So this is the idea of quantum active spaces, right? So the idea here is that I have a big system, and through some classical method, I'm able to figure out which parts of this big system require more classical computational resources, and then so treat whatever part of the big system is not into this active space with a computationally less demanding classical methods, and then spend most of the computational classical resources to tackle the hard part of the problem, right? Well, you can do that with a quantum computer as well. So the idea is that instead of using a high accuracy classical computational methods to treat the degrees of freedom of your system that require a very high accuracy, we can just use a quantum computer. Okay, which brings me to the next idea. So there's a lot of classical methods that are able to tell us which parts of the system should be treated with more accuracy, but all these classical methods like quantum computational tools coming from quantum information have never been considered to tackle these problems, right? So something that we are working on, we are trying to understand the power of tools coming out from quantum computation to the process to massage and process quantum problems, right? So even both from the quantum and the classical side. So we know that the performance of both quantum and classical computational methods depend heavily on the basis that we choose to address that problem, and there is a variety of classical techniques that we can use to massage our quantum problem in a basis for which that problem will be more easily addressed by classical techniques and also quantum techniques, but we have some examples of that. For example, we have Schrieffer-Wolff transformations or couple cluster expansions or transcorrelated Hamiltonian. So these are all classical methods that try to express the problem in a basis such that the computations are more easily done, right? But then the questions that we have asked ourselves recently is what happens if we start to use tools from quantum computations to do this exact task, right? So a tool that we have available from quantum information is Clifford transformations, right? So Clifford transformations are classically efficient, can be simulated efficiently with a classical computer. And so we asked ourselves the question, how can Clifford transformations help in representing our quantum problem, especially if they can express a quantum problem in a basis which will make quantum and classical computations easier to be performed to tackle that problem, right? So how do we do this? So imagine that you have a quantum Hamiltonian, which is a linear combination of Pauli operators, and imagine that this is a chemistry Hamiltonian. So a Hamiltonian with energy scales, the Hamiltonian that spans many energy scales. So what we can do is we can truncate this Hamiltonian at different energy thresholds, and we can throw away Pauli operators that don't meet that energy threshold. And then we can then efficiently find symmetries for these truncated Hamiltonians for each energy thresholds. And then once we find symmetries, we can define Clifford transformations associated to those symmetries that block diagonalize that Hamiltonian for every value of this threshold. And then once we have done with this, we can take the terms that we are truncated and put them back. So the outcome, so the result of this completely classical processing is that the resulting Hamiltonian is now approximately block diagonal. So we have this block diagonal structure, and in which smaller blocks are blocks where the quantum degrees of freedom are very strongly interacting, and as we go to larger and larger blocks, we have less weaker and weaker interactions. Okay, and then we realized that this structure was extremely helpful both for quantum and classical computations. In fact, something we know that speaking about classical computations, we know that a critical quantity to estimate runtime of classical computations, such as DMRG, is the bipartite entanglement of a state across partitions. So we found that we know that even modest improvement in this quantity can lead to massive speed up, because the classical computational overhead depends exponentially on this quantity, which is the bipartite entanglement. So what we did is we used this block diagonal structure to figure out a way of distributing the qubits that we have in our system on a 1D line, and then run the MRG on this system, which was ordered informed by this block diagonal structure. And what we observed is that in this new basis, the system had a very much lowered bipartite entanglement across different sections. And then we asked our computational chemist friends from Caltech, whereas with the existing classical methods we could achieve such improvements in the bipartite entanglement, and we found that state-of-the-art classical methods could not achieve this much of improvement for the bipartite entanglement entropy. And so this is an example of how ideas from quantum information can and classical processing can help. Classical computations, and we saw the same advantages when we tried to run, for example, VQE on a Hamiltonian expressed in this approximate block diagonal form. We reached the ground state for this lithium hydride Hamiltonian with only depth 2 within the spaces, which was something we could not do in the original basis. Okay, so I hope I've convinced you that there's a lot of interesting ideas and research opportunities if you think about the interface of quantum and classical computations, and which is, I guess, is the idea of this workshop. So with this, I'd like to thank you, and this is a summary outline of the topics I've talked about.
Thank you so much, Antonio, for the nice talk and for so many examples. So we are running a little bit behind, but maybe we have time for one question for Antonio.
So can I ask about circuit cutting? So I think that if we can cut the quantum circuit into two parts by cutting only a few bonds, then in that case, the entanglement between the two parts are so small if we consider, for example, BQE. So can we find a practical application where we can observe the quantum advantage in that case?
Yes, I think people haven't thought about that yet, but that would be definitely something that would be interesting to look at. We have all these techniques, circuit cutting or even entanglement forging, so we know that the tool is there, but I think what is not clear is how to optimally perform these cuts, or how do we understand, like given a quantum problem, how do we understand where to put quantum and classical degrees of freedom? I think that's very much an open avenue.
So I naively feel that the entanglement reduction technique may fit to the circuit cutting. So by approximating block diagram structure, we can find some weak entanglement between the blocks, and so we can merge like this.
Oh yes. Yeah, that is one way. Obviously, if you have this block diagonal structure, now there's many things many applications for this, right? So one will be, for example, you can think of these smaller blocks. You can take these smaller blocks and use that as your active space. Some other things that you can do, yes, now you can use, again, these blocks you can cut along these like larger blocks, for sure.
Thank you very much.
All right, thank you so much. So let's thank Antonio again